For the next couple of minutes, but it's a pleasure to introduce today's seminar speaker, Siyao Xu, who is a new member at the IAS. She's come as a Hubble Fellow. This is actually her second Hubble Fellowship. She got her PhD in 2017 from Peking University, and then was a Hubble Fellow at the University of Wisconsin, and is now starting her second fellowship here at the IAS. So we'll be here for the next 3 years. And as someone who appears at the IAS in some form or another every, I don't know, 5 to 10 years, it's kind of interesting to see how different sort of areas of concentration and specialty, particularly among the postdoc groups, sort of appear and then spread out across the world. I think that in looking at the members this year, I'm struck by the number and strength of people who are working at intersections of plasma physics and astrophysics. And Siyao is very much in that tradition. So we look forward to hearing from her. And as a reminder, for those who'd like to participate in a more detailed follow-up discussion, we'll have that today at 3 p.m. And I sent the link by email, but I'll also copy it into the chat in a few minutes, and I encourage anyone who would like to delve further into these topics to join us for that. So with that, I will turn things over to Siyao.
Thank you so much, David. Let me share my screen. Okay. So today I'm going to talk about turbulence. Honestly, except in research, I usually don't like turbulence so much, especially on plane. But turbulence is everywhere in daily life in all types of fluid flows. In astrophysics, turbulence is also very common. It participates in a variety of astrophysical fundamental processes, from transport of cosmic rays, like acceleration of particles, heating, to star formation, and amplification of cosmic magnetic fields. For example, MHD turbulence is a critical physical ingredient of cosmic ray study. After 1 century of their discovery, many things about cosmic rays still remain mystery. We performed the first numerical testing of a modern theory of cosmic ray diffusion in realistic MHD turbulence. And we also developed a new theory on cosmic ray diffusion in partially ionized medium. The theories on cosmic rays and particles in MHD turbulence are very useful for us to explain observational puzzles in a variety of astrophysical environments. Turbulence also accounts for magnetization of most astrophysical medium, where a process called turbulent dynamo. The theories on nonlinear turbulent dynamo and dynamo in partially ionized medium are very helpful for us to understand the origin of magnetic fields and their roles in different astrophysical systems. So, I'm not going to talk about these theories on turbulence today, but I'm very happy to have interaction with you on different subjects, and we can talk later. Today, I'm going to show some new observational evidence for turbulence in universe. Although I'm a theorist, but you will hear a perspective from a theorist on some observations. The turbulent nature of astrophysical media is evident from observations. In the intergalactic medium, turbulence can be driven by shocks due to accretion of gas from voids to filaments. In the intracluster medium, mergers of clusters can induce turbulence. In the interstellar medium, stellar feedback, supernova explosions can drive turbulence. In the interplanetary medium, star-stellar wind provides source for turbulence. The fundamental physics of turbulence is statistics. The statistical measurement of velocity, density, magnetic field fluctuations induced by turbulence show a parallel spectrum of turbulence in different astrophysical medium over a vast range of length scales. This parallel spectrum of turbulence, physically, it comes from turbulent energy cascade. Similar to water cascade, turbulent energy injected at large length scale cascades down towards smaller and smaller length scale until the energy dissipated at the smallest length scale. And along this energy cascade, turbulent energy passed down from one size eddy to next smaller size eddy with a constant energy transfer rate. So this turbulent velocity and this turbulent kinetic energy, and this is the time scale for the eddy over time. This is the size of the eddy. So the constant energy transfer rate of turbulence directly gives this 5/3 cosmograph parallel spectrum for turbulence. So the parallel spectrum is described in terms of wave number. So this is large scale and this side is small scale. Since I'm going to talk about this parallel index a lot, I would like to draw attention that for cosmograph scaling, one-dimensional index is 5/3, so three-dimensional is 11/3. For the interstellar medium in our galaxy, there's a so-called big or grand parallel in the sky, which is a composite parallel spectrum of electron density fluctuations spanning over many orders of magnitude in length scales obtained from different observations. And these observations include high latitude diffuse H-alpha emission for the large scale parts, scintillations and scattering of nearby pulsars in local ISM for the smaller scale parts, and in situ observations of Voyager 1 for very small scales. This spectra extends from 50 meter to 10 to 70 meter. And is consistent with cosmograph scaling, most part of it, except for the enhanced power here you see in the kinetic region on very small scales. I should also stress that this grand parallel spectrum measure is for the warm ionized medium. In fact, except the diffuse H-alpha emission, these observations from nearby pulsars and spacecraft are all for local ISM, which has similar environment as the warm ionized medium with relatively smooth density distribution. So this is for the warm medium. If we move to colder and denser interstellar medium, and we will see significant departure from the cosmograph scaling for density spectra, and this is 3D density spectral indices. These are traced by cold gas tracers like H1 absorption, dust, CO. And you see their indices are significantly smaller than the cosmograph ones seen in warm gas. And the reason for this is that in the multi-phase SM, turbulence has different properties in different interstellar phases. In the warm ionized medium, turbulence is subsonic to transonic. Density fluctuations behave as a passive scalar. They are passively stirred and mixed by turbulent velocities. And here as a numerical experiment, we show how density fluctuations evolve in the turbulent velocity field. And you see the density distribution becomes more and more homogeneous. And the density spectra follow the same Kolmogorov spectra as turbulent velocity. In the code, it's stuck here. In the cold interstellar phases with the turbulence speed exceeding sound speed, turbulence becomes supersonic or even highly supersonic. Supersonic turbulence, we know, is dominated by shocks. And this shock compression drives density enhancement toward smaller scales, and that gives the shallowness of density spectrum. This is density spectrum measured in highly supersonic simulation. Interestingly, if they use a logarithm of density, which removes the density peaks in the distribution, and they found a steeper spectrum similar to the Kolmogorov one.
And it's minus 5/3 here rather than 11/3 because this is a 2D simulation? Or
No, it's 3D. So the turbulence simulations are show as 3D, but they show 1D spectrum.
Okay, thank you.
Yeah. We can use sonic Mach number to quantify turbulence speed relative to sound speed. And from warm to cold interstellar phases with the increase of sonic Mach number, and you see the density distribution changes from homogeneous to more clumpy. The density spectra changes from steep to shallow. You see the density peaks appearing in the supersonic turbulence in cold interstellar phases like molecular clouds. In fact, these are the seeds for gravitational collapse and star formation. It means that these dense regions can become dense and stable and form pre-stellar cores.
Do these simulations include self-gravity?
No. This simple simulation back to 2007, well, I shouldn't say simple, but it's not designed for star formation study. It is for MHD turbulence study to see the effect of sonic Mach number on density statistics. But there are many star formation simulations show that in this shocked compressed region and the subsequent star formation happens.
Thank you.
In the collapsing core, dense core in a molecular cloud, when the gravity takes over, gravity can drive additional turbulence. And by comparing the case without turbulence and with gravity-driven turbulence in a collapsing core, we found the presence of turbulence can significantly affect the infall velocity, the density distribution, accretion rates, diffusion of magnetic fields in the collapsing core. So it can significantly affect the star formation process. So these are some introduction of turbulence spectra. Today I'm going to talk about some new methods to measure turbulence spectrum. Although I showed some observations, it is not easy to measure turbulence. There exist different techniques, but few velocity clean and reliable turbulent velocity spectra measurements are available. For density spectra, which are much more easily accessible to observations, but observations are usually for a particular region of sky, a particular molecular cloud, or using a particular gas tracer. So is there a way for us to more easily get turbulent velocity spectrum? And is there a way for us to get simultaneously different density spectra in different interstellar phases? So with this motivation, we have explored point sources as new tracers of turbulence. And this is different from earlier measurements using spatially continuous emission from gas. There are two types of point sources. The first type, I use this illustration. These point sources, they are moved around by surrounding turbulent motions, and their velocities are coupled to the turbulent motions of the background gas. So in this case, by measuring the velocities of the point sources, we can get statistics of the turbulent velocities. Another type of point sources, they are not directly affected by turbulent motions, but their signals travel through a turbulent medium to reach the observer. So the propagation effect caused by turbulence can be used to measure, in most cases, density spectra in the turbulence medium. Okay, so let's first look at the first type of point sources. Some examples are dense cores in molecular clouds and even stars in molecular clouds, and filaments in the center of galaxy clusters. So the velocities of these discrete objects reflect the turbulent velocities of the surrounding gas. So this is the turbulent velocity spectra measured using the motions of dense cores in Taurus cloud by Qian et al. 2018. And they found the velocity spectra. So this I showed in real space. They showed in real space. So on large scale, they found that velocity spectra is consistent with Kolmogorov scaling, 3D. And smaller scales, it steepens. And we found that this shows that the solenoidal turbulent motions on large scales immerse the volume of the Taurus cloud. And on small scales, this steepening shows compressive motions traced by these dense cores on small scales in a small fraction of the cloud volume. The transition between these two different scalings gives the typical size of the core cluster. And here, the lower part shows another observation showing the velocity spectra measured using the motions of filaments in centers of several nearby galaxy clusters led by Li 2020. And we found that the driving scale of turbulence coincides with the size of the bubbles inflated by supermassive black hole driven jets. So it indicates that the supermassive black hole provide the energy source for turbulence. And this driven turbulence plays the role as a channel to couple the feedback to surrounding environments. And also the turbulence amplitude measured using the motions of these cold filaments is also consistent with that measured using X-ray emission from hot gas, showing the coupling between the cold filaments and hot gas in centers of galaxy clusters. Okay, this is the first type of point sources. The second type of point sources are usually radial point sources, for example, pulsars. The propagation effect includes scattering and scintillation. This happens when the radio waves from a pulsar interact with electron density fluctuations, and that can give fluctuations in intensity. They're similar to the twinkling of stars we see at optical wavelengths. Other scattering observable, including a broadening of pulse from pulsar, and that I will discuss later. Another one is Faraday rotation. So from the rotation measure statistics, people can get statistical information on electron density and line side components of magnetic field fluctuations. Another one is dispersion measure. Well, we know light is dispersed in SM. This causes a delay of pulse arrival time. And this delay depends on frequency. So the delay is larger for lower frequency light. It arrives later for lower frequency. And we use dispersion measure to quantify the amount of electrons between the observer and the pulsar. So it's defined as the integrated column density of free electrons along the line side. Among these three methods, in fact, the first two methods are not new. For example, the scattering scintillation has been used to obtain information on interstellar density spectra for 50 years already. And also, if you remember the grand power law in the sky that I showed at the very beginning, part of it comes from such measurement. But I would like to show some new findings that we got by using these existing methods first. Let's first look at scatter broadening of pulsars. The pulse from a pulsar can be temporarily broadened because of effect called multipath scattering in ASM. Okay, so this is, I think, is a better illustration. The signal from a pulsar, they travel along different paths with different lengths, and they arrive at observer at different time. Note that this effect is different from the dispersion effect. As a result, the pulse is broadened, is smeared with a scattering tail. From the scattering measurement, we can get information on the underlying density fluctuations. It was found that for low dispersion measure, remember that dispersion measure depends on both the distance of the pulsar and the electron density. It is found that for low DM pulsars, which are usually observed at high latitude from low density region sky, for these pulsars, their scattering behavior is consistent with the cosmograph expectation. But for high DM pulsars, these orange dots, they are mainly observed near the galactic plane from high density region of sky. Their scattering behavior shows significant departure from the cosmograph expectation. And this has been a puzzle in radio astronomy. From the scattering measurements, this is scattering time, the scatter broadening time as a function of dispersion measures of pulsars. Of around 100 pulsars in this observation, we first identified a shallow density spectrum, which can well explain the enhanced scattering of high DM pulsars. The shallow density spectra that we found has the index, this is a 3D index 2.6. It's much smaller than the 11/3 for cosmograph scaling. So this, and if you remember, this is also consistent with the shallow density spectra measured using cold gas tracers. So this suggests the contribution of supersonic turbulence in cold interstellar phases in disk where the pulsar signals travel through. Let's look at another method using rotation measure statistics. So the rotation measure fluctuations, people usually think they can provide information on magnetic field fluctuations. For example, this is an early measurement by Minter Spangler, 1996. They used 38 extragalactic sources to measure the structure function of rotation measures. We found that for this part at large angular separations, it can again be explained by a shallow density spectrum, with the spectral index also very similar to what we got from the scattering measurements of pulsars. So at least for these observations, it suggests that the rotation measure fluctuations is mainly dominated by density fluctuations instead of magnetic field fluctuations. Okay, so now let's move to The third method. So this is a new method. People usually use dispersion measure to model distribution of electrons in our galaxy. But here we use dispersion measure in a statistical way to learn the nature of electron density fluctuations and interstellar turbulence. There are around 2,700 pulsars on the sky. You see that this is a sky map of these pulsars. They are mainly distributed in the galactic disk toward inner galaxy. And this large number of pulsars enable sufficient sampling of the SM by different line sight toward these pulsars. On the left, I show the sky map of H alpha emission to illustrate the density structures in the warm ionized medium. And this includes both discrete H2 regions in the disk and more diffuse warm medium at high latitude. But we know that the signals from pulsars, they not only travel through the warm ionized medium, they also travel through the cold interstellar phases in the disk. So we use the structure function of DMs of pulsars to get information of the underlying electron density fluctuations. This is the correlation function, and it is characterized by turbulence parameters. This is related to the slope of the density spectrum, and this is the correlation length of the spectrum. And the correlation function is also directly related to the power law spectrum of density fluctuations. The structure function is defined as the average of the squared difference between DMs of a pair of pulsars. So X are their locations on the sky, and they are separated by this angular separation. The average is done for all pulsars at the same angular separation. So we can get structure function measurement as a function of angular separation.
So what do you do about the uncertainties in the distance? Because the distances to pulsars are notoriously difficult to get. I mean, you can get them from VLBI, but as far as I understand, the only other method is just to use dispersion measures themselves and the maps of the electron distribution in the galaxy. So how do you go about these things?
Indeed, people, there are several models, as I said, they use the DMs to get electron distribution of our galaxy. So in this case, there's assumption that, the DMs depend on both distance and electron density. There's an underlying assumption that we only assume the electron density fluctuations are regulated by turbulent motions. Well, I think it's reasonable because there's no reason to think about the distances follow some power law spectral distribution. So the distances, they get involved as some noise. So they add some noise level. Let me show this. So how we relate this structure function of projected quantities to the three-dimensional fluctuations of the quantities. And this has been discussed in detail by Lazar and Pogerson in 2016. In that case, they were studying synchrotron, which is spatially continuous emission, but we extended to statistical study using point sources. Let me see, you can, okay, if you follow these equations, so just a bit detail here. You see the L1, L2, these are the distances. They come into the equation, the distances of the point sources. And at the end, they appear as this term. This is a difference in distances of different point sources. So the spectral scaling, if there is a turbulent motion, this spectral scaling would appear in this term, and this term appear like noise. And of course, if you have two high level of noise, it will not be able to see the signal term. So this has been taken care in these calculations. We can come back to this later if you're interested to know more details about this calculation. It's a bit complicated depending on different turbulence region, depending on the geometry of the turbulent volume.
It seems to me that, you know, this term, if the distances are determined from the dispersion measure, then this term should be somehow correlated with the first term. I mean, the first term is due to the dispersion measure, and the second one, you know, the distances are determined based on that.
Yeah, I mean, the first term is here, and you can see that there is a gain. It appears, you're right, it again appears here as this second term of the first term. And only this one, you see it is related to the density spectrum induced by turbulence. So yes, so okay, you can see that this is the mean electron density that we use. It's not even for the turbulent electron density. So the electron density can have non-turbulent component, turbulent component.
Mm-hmm.
So this noise from distances enter in both this term here and also this term here. Okay, so we first measure the structure function of DMs of all pulsars for the entire sky. We don't see much. It's like noise with flight structure function. This is because of the contamination from the disk, from the spiral arms, H2 regions. Obviously, these are not turbulent structure. So we realized that if we want to see some turbulence information, we need to go a bit higher latitude. So at latitude larger than 5 degrees, we again measure the structure function of DMs. And then we see it indicates a shallow density spectrum with the spectral index 2.2 over length scales from 80 to 800 parsec. Compared to earlier measurements using cold gas tracers for individual molecular clouds, this spectra we obtain from pulsars, all sky pulsars on larger length scales. And the spectral index is even shallower than that in cold phases. But we know that this can be again affected by the contamination along the path because of these non-turbulent structures towards smaller scales. So this is for shallow density spectrum measurement. We also have the prior knowledge that in the diffuse warm ionized medium, we expect to see cosmograph density spectra based on H-alpha emission. To be able to detect the diffuse warm ionized medium, we select a region sky which is off the galactic plane toward outer galaxy. And then we measure the structure function of DMs. We found a short range, inertial range of cosmograph density spectrum with large uncertainties. The large uncertainties, this is because you see in the diffuse warm ionized medium, it is not preferentially populated by pulsars as we see. So we don't really have a sufficiently large sample size, so the uncertainties here are large. The scales here we get, this is the correlation length of the turbulence on the order of 100 parsec. It is consistent with what we expect for interstellar turbulence driven by supernova explosions. So
yeah, I think Sukanya has a hand up.
Yeah, this is related to something a few slides back when we were talking about distances and in line with the question that was already asked. So some fraction of this, not a large fraction, but some fraction do have distances from pulsar timing as observed by, nanograph, PBTA, and the other arrays. and an even smaller fraction have distances from Gaia, okay, right, if they have white dwarf companions. So for that subset, have you looked to see, can you constrain the noise that you have from the distance term?
Sorry, you see, I can get information on the density structures along the path?
I can maybe explain this later. I don't want to interrupt your talk, but for some subset of these, you do have more or less reliable distances. And so for example, some of these have white dwarf companions, so you can get parallaxes from Gaia. And for the others, again, a smaller fraction than your total set, you have distances from pulsar timing, from nanograph, and the other pulsar timing array measurements. So one could, in principle, compare what you're doing, the reference that you cited, I forget exactly what it was, but one of the Lazarian references to these distance measures.
Okay. I'm not sure.
Sorry, too detailed a question.
Yeah, I'm not sure if we understand what we talk about later, but yes, it would be nice if we can really improve this measurement to have more clean measurements. Okay, another interesting feature we see that on larger angular separations, and you see another parallel here. This in fact can also be seen for the entire range of longitude, but at even higher latitude, at larger than 10 degrees. And you see again this parallel spectra appearing at large angular separations. And this indicates deep density spectra with one-dimensional index 1.3. This is a bit smaller than the 5/3 cosmograph slope. And it is on scales from 900 parsec to 4 kiloparsec. And if you remember, these scales are much larger than what we expect for interstellar turbulence driven by supernova explosions on the order of hundreds parsec and below. So this is very large scale, galactic scale density spectra, which hasn't seen earlier from measurements in our galaxy. But such galactic turbulence spectrum, a similar galactic turbulence spectrum have been seen in both galaxy simulations and observations of external galaxies, both disk galaxies and dwarf galaxies. And both observations and simulations suggest that for this galactic turbulence, the gravitational instability and self-gravity in the disk can be the ultimate energy source. If this is also the case for our Milky Way, then the interesting questions are, what is the role does this large-scale turbulence play in the SM, and what is its interaction with the smaller scale interstellar turbulence? So these are open questions that we don't know. So let me summarize this part of my talk. Okay, I'll speed up a bit. So I like to use this illustration to statistically describe the density distribution in our galaxy with both diffuse warm medium, with subsonic turbulence and cosmograph density spectrum, and these cold interstellar phases with supersonic turbulence and shallow density spectrum. Both are seen using our new approach with DMs of pulsars without invoking multiple tracers. I should stress that the DMs of pulsars probe the ionized component of the SM. The similarity we see in terms of the shallow density spectra measured using cold gas tracers, neutrals, shows that the coupling between ionized and neutral component of SM over a broad range of length scales, as would we expect for partially ionized medium. In addition, we also found a galactic scale density spectra in the diffuse warm ionized medium, which hasn't been seen before from observations in our galaxy. I think it would be interesting to further explore whether such turbulence plays a role in the history of our galaxy, whether it affects its formation, evolution, gas dynamics, and star formation. Okay, so I haven't.
Before you proceed, you had this very nice slide where you summarized, the 3 different ways of probing, the turbulence. Can you pinpoint which particular methods are sensitive to turbulence at which scales? So which ones are probing small scales? I would think like broadening and scattering may be more sensitive to, smallish scales, whereas dispersion measure method could be more sensitive to like kiloparsec scales. But is this a more or less reasonable understanding?
Yeah. So I have to say that this method using DMs of pulsars, it cannot really probe small scales, because you see when every time you go small scale, there are a lot of noise. And this effect, because every time when we do the integral along the line side, there's just a lot of noise coming from the past, all these different density structures that are non-turbulent. So let's see, for the second one, this Kolmogorov spectrum, I would think that using diffuse H alpha emission from high latitude is a better way, because it's cleaner. And for another method I showed with scattering the scintillation, that can also be used to measure the diffuse SM. But the observation done by Armstrong et al. Was only for nearby SM within 1 kiloparsec. So I don't know, maybe people should update this result using more distant pulsars, but to see whether it can be used to get a big pearl in the sky for the larger range of distances. And the scattering, the angular broadening that I mentioned, temporal broadening that I mentioned, which is indeed very sensitive to smaller scale density structures. But unfortunately, we cannot get direct information on the length scale, because this is dispersion measure, it's not length scale. But we found in our paper that the length scale could be as small as some parameter study shows as small as, if I remember right, is 10 to 7 meter, which is basically the inner scale of the density spectra. And it's because it's shallow, it has to enhance the density enhancement at a small scale, which is most powerful for giving the large scattering that we observe from this effect. So I would say the best way is to use different techniques synergetically to get the spectrum in different regions of sky, and also for different interstellar phases and over different ranges of scales.
Has anyone looked at the temporal variability of the dispersion measure of pulsars? Because as they move, at a velocity of hundreds of kilometers per second in the plane of the sky, you would expect to probe these small scale fluctuations on AU scale. I mean, you would have variations in the dispersion measure due to that. I mean, maybe you're going to talk about this, I don't know.
Yeah, in Armstrong et al., they use the DM fluctuations of a few pulsars with time.
Okay.
Yeah, and I think some part of a small part of it. So there's different colors, so represent different observational methods, and they find what is the dominant wavelength corresponding to this measurement, and they get this composite spectrum. So yeah, they have used this method.
Thanks.
Okay, so let me quickly, so I just want to mention very quickly that I haven't mentioned the magnetic energy spectra yet. In fact, using point sources like pulsars and combining rotation measure and dispersion measure, one can get magnetic energy spectrum. And this has been done by Han et al. 2004. They found a very flight magnetic energy spectra on very large scales, half to 15 kiloparsec in our galaxy. So this is done in 2004. I think it should also be updated because now we have more available rotation measures of pulsars to see whether we can get a more extended spectrum on smaller scales. In their original paper, they placed this mean-to-spangler measurement here, but as I said, this is not from magnetic field fluctuations, especially for the shallow parts. We think it is more like density fluctuation contribution. Okay, let's move beyond our galaxy. You remember these are two types of point sources that I discussed. For the second type of point sources, if these are extragalactic point sources like fast radio bursts, then we wonder whether they can be used to probe turbulence beyond our galaxy in the intergalactic medium. Fast radio bursts are very powerful radio transients. Their dispersion measures are found to be much larger than that of pulsars at similar galactic latitude. So it means that their DMs cannot be explained only by the galactic component. It's mainly come from extragalactic DMs. And also from their sky distribution of FRBs, and you can see it's basically isotropic. So based on these facts, people believe that FRBs are of extragalactic or even cosmological origin. And in fact, the DMs of FRBs have been suggested to measure the baryons to find missing baryons in the local warm, hot intergalactic medium. But here we again use their DMs in a statistical way to probe electron density fluctuations in the intergalactic medium. We again use structure function of their DMs. Well, we know that the fluctuations, density fluctuations in their host galaxies are not correlated. So their structure functions can be either used to probe the turbulence in our galaxy or the turbulence in the diffuse intergalactic medium. So between these two scenarios, before our analysis, we really believe that this should be the case, just based on our knowledge of the intergalactic, interstellar turbulence in our galaxy and lack of knowledge of turbulence in the intergalactic medium. But very surprisingly, after we measure the structure function of DMs of FRBs, we found a rising power law scaling of the structure function. This cannot be explained by the galactic DMs or the galactic turbulence. And in fact, from this comparison, you can see that the structure function we get from extragalactic DMs are very similar to that we got from total DMs. So this mainly comes from extragalactic DMs. This correlated large extragalactic DMs indicate power law spectrum of electron densities, which is consistent with the homograph one in the intergalactic medium. It suggests the existence of turbulence in the intergalactic medium on large scales up to on the order of 100 megaparsec. We get this estimate of the correlation length using the angular separation where the structure function starts to saturate and the distances of FRBs. And you see the measurements have large uncertainties because currently we only have around 100 FRBs publicly available. So in future, we definitely need use more FRBs, thousands, hundreds, thousands FRBs to have a more definitive test of this result. So if this finding is true, let's tentatively place this result in the big picture of turbulence measurement in the universe. There's a spectral index as a function of length scale. This extended one is the big power law in the sky that I showed at the very beginning for our Milky Way. up to tenths of a parsec. And in fact, here, based on our new measurement, we can have another power law extending to several kiloparsec based on the density spectral measurement, although it has a different index. On larger scales in intracluster medium, there are turbulence measurement up to scales of hundreds of kiloparsec. And this new finding using DMs FRBs show new evidence of turbulence even on larger scales. I said this is really surprising because there was new earlier measurement from both simulations and observations, so show turbulence on such large scales, which is in fact already comparable to the size of super galaxy superclusters. Okay, so let me summarize. I discussed several methods of measuring turbulence spectra in diverse astrophysical medium and over different ranges of length scales, including velocity spectra obtained from dense cores in molecular clouds and dense filaments in the center of galaxy clusters, and non-universal density spectra we obtain from the multi-phase interstellar medium over different ranges length scales. For the intergalactic medium, our results show that FRBs can be used as a new unique tool to probe large-scale turbulence in the intergalactic medium. Okay, I will stop here. Thank you.
Okay, thanks very much. We have time for a few more questions. And I think you could just unmute and jump in. Sukanya, you have your hand up. I'm not sure if that's from before, but do you want to start?
Yeah, so I think you mentioned that some of these FRBs aren't localized. And I wonder, you know, for at least those, if you were to sort of perform a, you know, dropout analysis, like if you were looking at a subsample of the full set of FRBs, would that possibly, you know, some of those may have smaller errors because for example, localized ones where you know the host galaxies and you can get a redshift. So I wonder if you've done that.
So first of all, we only have, so when I published this paper, we only used 112 FRBs. The statistics is already, the sample size is already too small to have, let's say, just a fraction of these FRBs, because then it's not reliable. And also the uncertainties here I put is purely comes from the sample size. So when the sample size is small, the uncertainty is large. It's not from the estimate of the distance. In fact, this measurement, because this is already a structure function of projected quantity, the DMs, there is no distance information involved here. We only use the distance estimate, not individually, but from their PDF, from their distribution. We find the peak of their distribution of the FRB distances. We only use the peak to estimate what is the corresponding redshift, and then get estimate of the distance. Yeah, and then
earlier for the pulsars, you know, some of these have white dwarf companions, and they do have parallaxes from Gaia, so you do have very reliable distances for that set. And some of them have timing measurements from, you know, nanograv and PPTA and EPTA. So those are also fairly reliable distances. So, you know, for the pulsars, you could look to see if those distances improve your
yeah, so I understand. I mean, if in observations, we usually deal with projected quantities, and that's why we use such statistical measurements using structure function of DMs. If in a case that we have 3D position, for example, now we are analyzing stars, and some stars, if they have 3D position information available, we can directly get 3D velocity spectra, 3D turbulence spectra. We don't need this technique anymore because this is only for projected quantities when we don't have 3D information. Yes, when we have 3D information for some pulsars, then we can take out this sample to directly get 3D density spectra, and that is much better. So this is just for the case for the large sample and that without distance measurements.
Okay.
Matthias, you want to go next?
Sure. Before I ask my question, can you tell me exactly what this structure function is? Is this just a 2-point correlation function, something like that?
Yes, their structure function is related to correlation function. Yeah, where is it? So it
okay.
has
Sounds good. So the 2-point correlation function. So in the case that you were just discussing of the DMs of the FRBs, so what is your measured value? What kind of density fluctuations do they imply? I'm just saying that it seems to me that at 100 megaparsecs, we know very well how the matter is distributed. This is super large scales. So one should be able to compute this from the cosmological model. I don't know if this would be yeah. So I just wanted to get a sense.
So we can even see this by eye. You see that for the correlation scale, which correspond to the largest density perturbation level, and this is basically squared of the DMs, so 10 to 6. And the distance here, I think at the co-moving distance is around 1000 megaparsec. So
right, but this is a measurement of the fluctuations, right? So are we talking about, is the claim that the density fluctuates by 1% and smooth of 100 megaparsec, by 10%, 100%? What is...
I need to look at the number. I may tell you a bit later. Yeah, I should check that because I didn't really disentangle the distance and the fluctuation value.
Can I ask a related question, which is what's the interpretation of what happens at large angles where this goes flat? Is that I was sort of expecting that you would have something at large scales and then this would go up at small scales, at small angles, and so I'm trying to.
Yeah, so it's just.
Are you subtracting the mean, or maybe she's not subtracting the mean, and then this is just d square, the uncorrelated d's,
yeah,
the two directions.
This just means it becomes uncorrelated, so it should saturate.
Because she's not subtracting, it's not delta d, it's just d. So you get the product of the two.
No, but d was a difference between two. Your structure function is a difference between dispersion measure at two different angles. Is that right? So, I mean, is the interpretation that at large scales, this is just what's coming due to distance variations of the fast radio bursts, or?
No, I think the thing is, if it just comes from the different distances, we don't expect to see the parallel scaling at all. We just see some flight structure function over all angular separations, because y distances should follow any parallel shape. So we think this comes from the electron density fluctuations. And then this here, it becomes the uncorrelated. So
okay, so you've got small structures, but they're no longer correlated with each other.
But so then why this structure function decays? That's, I guess, your confusion. Usually when we look at this in cosmology on small scales, there's more fluctuations, so the thing goes up, not down.
So I think it's here that if you're closer together on the sky, then you're probing similar structure, and so the actual variations themselves are smaller. So it's a different. Yeah, it's a different kind of statistic from the one.
Yeah, probably different, because this shows the turbulent fluctuation, and we know the turbulent energy is smaller at smaller scale. So, so the fluctuation level should be smaller at smaller scale.
Okay, Renyu?
I had a similar question actually like Matthias, but let me just ask a different way. All you're measuring is just density fluctuations of power spectrum. And how should I think about the velocity structure in this quote turbulence?
Velocity can be measured where I showed here. These are the velocity spectrum. So you can
Right,
also measure structure function. Mm-hmm.
But for the FRB case, you have no such measurement, right?
I don't. So I don't know. So this method is using the propagation effect. So it's not because of the movement of FRBs. And
Understand, yeah.
yeah, so I don't know how to get velocity information in the medium.
I mean, at 100 megaparsec, they are causally unconnected, except at inflation.
Sorry, they are got.
Well, so I think that what Renyu and Matthias and I are all getting at in different ways is the so usually when we think of turbulence, right, we think of turnovers and eddies, and once we get to scales of 100 megaparsecs or even 20 megaparsecs at the kind of velocities that you get, there isn't actually time for a single turnover in the age of the universe. And so in that sense, it's kind of sitting out here on this scale, but I think that at least coming from the large scale structure perspective, we would say more that this is now a different kind of phenomenon. You've got density structure that's imprinted by the gravitational growth of the primordial fluctuations, and that's producing these kinds of variations. But maybe we shouldn't at these scales be calling it turbulence, although it's kind of interesting if it sits on some continuation going from, I think in the intracluster medium, you've really got turbulent motions, and it makes sense to still think of it as turbulence. It's an interesting result if you extrapolate from the clusters and you actually predict what you get in large scale structure, but it sort of seems as though this would be a coincidence because you no longer have time for actual, kind of full turnover motions on those scales.
Yeah, I don't really know what is the origin for this parallel electron density fluctuations that we see, whether it's driven by turbulence or some primordial origin. That this is very surprising to me. Yeah, I just don't know how to explain it.
Well, in cosmology we have, right? We have density fluctuations. We have established on these large scales its power spectrum. We have measured it in various components, and this 2-point function is just an integral of this power spectrum that we claim to know. So, we could have done this integral and give you something which I don't know the units, I don't understand, but presumably it should work.
Does it have larger fluctuations on larger scales?
Yeah, it's a power law that goes all the way to very large scales. I
think it should be right that the people, including people here who are doing calculations of things like the Sunyaev-Zeldovich effect and so forth, we ought to be able to actually give you a prediction for what this should look like, and see whether it matches your observations. And so I think this would be
nice.
I think the language of it will be a large scale structure language rather than a turbulence language. But I think that this may be a new measurement that maybe people haven't actually tried to explain from cosmology, but that would be interesting to do.
Yeah,
I was wondering, related to this, the people that are trying to put the FRBs like in some sort of Hubble diagram with their DM and redshift. There's the scatter across it, and I remember. So isn't this related to that? Like the scatter of the DM with respect to it's just due to the density fluctuations, and there were some calculations. I need to take a look. Like maybe some paper where Kendrick Smith was. I don't know.
Matthias, some people use FRB as a standard candle, at least
Right.
for their purpose, not necessarily a DM measure. But just put the numbers in perspective. You're trying to translate your density power spectrum to this measure. So what's plotted here is DM measure squared.
Mm-hmm.
So if you integrate density 10 to the minus 7 today, electron, and to 1 gigaparsec, so you roughly get something like 300, maybe 2,000 in the series. So you square that, they give you 10 to 6. So it looks like the fluctuation is pretty large on the order.
Yeah, this sounds, we would say, not possible, right?
Yeah, that seems large.
Well, I think we all
should do.
We need to think a little bit about how this translates into a
there's the 1D
variance
version.
along scales of a given angular separation. So really, when you say 100 megaparsecs, basically, you're taking your angular separation of 10 degrees and multiplying by a sort of typical distance to the FRBs. Right? And so those interesting questions of whether those fluctuations get dominated by, the probability of hitting one or two fairly dense structures, or by, averaging over fairly large things. And I think that
so the assumption is
smaller structures nearby versus bigger structures further out.
So the assumption here is it's a statistically homogeneous, but it may not be the case. I don't know.
Right. Good. Okay, I think we should stop our Q&A for now. As I put into the chat, we'll have an opportunity for a conversation from 3 to 4 today, and I think we've got a lot of potential things to follow up. So I encourage people to join that if they can. And then also, if you'd like to sign up for a one-on-one meeting, there's a sign-up sheet for that, which I circulated earlier, or you can just email Siyao directly. And fortunately, there's lots of time to follow up all of these opportunities. So thank you very much for a wonderful and stimulating seminar. So long, everybody.
Thank you.
Yeah, thank you.
Bye-bye.